So in the last video, we talked all about acids. In this one, we are going to talk about bases. So once again, we have multiple definitions for what makes a base, depending upon the context. And the Arrhenius and Bronsted-Lowry definitions are still the two that we are going to stick with. So you'll notice that these are very much complementary to the definitions we gave for the acids. So an Arrhenius base is something that increases the hydroxide concentration in solution, in aqueous solution specifically. So this increases the OH minus concentration, which is the hydroxide ion in aqueous solution. And the Bronsted-Lowry definition, which I mentioned in the last video when we were writing the reaction for acids, since that involved a base, is that a base is something that accepts a hydrogen ion, aka a proton, from an acid. So with acids, we had this kind of nice clue to help us identify what is an acid. If we're looking at a formula, we need to have hydrogen, we need to have hydrogen involved in a polar bond, and typically the acidic hydrogens are written first in the formula. Unfortunately, we don't have such a convenient clue for bases. They are a much more structurally diverse group of compounds. So they can be harder to identify in some ways. Some of them aren't. Some of the most common bases that you will see are ionic compounds containing hydroxide. So when the anion is hydroxide, it makes sense that when that dissolves in aqueous solution, the hydroxide ion concentration would increase, since we know that ionic compounds split apart into their component ions. So anything that contains hydroxide as its anion is definitely a base, so those are pretty easy to identify, but there are many others as well that are less obvious. So our strong bases all fall into this category of hydroxide compounds. So the strong bases, once again, there's kind of a short list for anything strong, and then if it's not strong, it's weak. Same mentality kind of applies to bases as it did for acids. Once again, these are things that ionize completely, that every molecule, every unit of base in a solution exists in its ionized form. So these strong bases are all of our soluble hydroxide compounds. So if we refer back to the solubility rules, most hydroxides are not soluble, but a handful are. There are quite a few exceptions, which are the alkali metal hydroxides, so that's lithium hydroxide, sodium hydroxide, potassium hydroxide, etc., on down that column, as well as calcium, strontium, and barium hydroxides. So all of the soluble hydroxide compounds are considered to be strong bases, meaning that they do dissolve. Any ionic compound that dissolves splits into its ions. And for the strong bases, that is essentially all that really happens. So if we have a strong base let's say barium hydroxide in water, whatever barium hydroxide is actually dissolved exists as barium ions and hydroxide ions. So all of it that is able to dissolve, that is able to actually get into solution, exists in this separated ionized form, which is why we consider it to be a strong base. The weak bases are a very diverse category. So they can be tricky to identify, and we will talk more about it as we go through this unit. For now, you can assume that if it doesn't fit one of the other categories, it is probably a weak base. Going forward, you will need to recognize that not everything is an acid or a base. So really your choices are strong acid, strong base, weak base, or none of the above. For now, we're going to ignore the none of the above possibility. We'll get back to that. So these can be a little bit tough to identify in some situations. There is one in particular that is important, and I would like you to recognize specifically right now, which is NH3, which is known as ammonia. So this is far and away the most common weak base that you will encounter. It's really commonly used. It is really cheap. So that is why just one for now to work with to kind of get used to weak bases. And we'll expand our horizons later. So when ammonia reacts with water, and a similar reaction happens for all weak bases, it does actually react with the water, more similarly to acids. But now ammonia is our base, which is a proton acceptor. And water, in this case, is going to be functioning as an acid, which we know is a proton donor. So in this case, the ammonia is stealing an H+ from the water. So when water loses H and a positive charge, it goes from having 2 hydrogens to only 1 and goes from neutral to negatively charged. So we end up producing hydroxide, which is how we're increasing the hydroxide concentration to fit the Arrhenius definition of a base. And when ammonia gains an extra H and a positive charge, it becomes the ammonium ion, NH4+. So ammonium would be my conjugate acid in this reaction, since that's what my base turned into when it gained a proton. And hydroxide would be my conjugate base, since that is what my acid turned into after it lost a proton. So we'll see as we go throughout this unit that many nitrogen-containing compounds similar to ammonia are also weak bases. But not all of them. But nitrogen often acts as a good base. And many anions are also weak bases. But again, not all of them. And we'll learn to identify when an anion is a weak base versus when it is not a weak base in a couple videos from now.